All right, now back to part two of this little presentation with regression. So part two here we'll go to basic ideas of how we can tell just how far off our regression line may be, and just ways to look at how good a regression line actually is. So in working with two variables related by a regression equation, the marginal change in a variable is the amounts that it changes when the other variables change by exactly 1 unit. And so that actually can also be the slope b sub 1 in the regression equation, and that represents the marginal change and y that occurs when x changes by just 1 unit. And let's see, suppose for 40 pairs of shoe print lengths and heights, the regression equation was y hat equals 80.9 plus 3.22x. Now the slope of 3.22 tells us that if we increase the shoe print length by 1 centimeter, the predicted height of a person increases by 3.22 centimeters. Now this is a separate example from the previous example with the 5 shoe prints and heights, which that equation was 125 plus 1.73x. So that one changed by 1.73. This is just a different hypothetical example if we had 40 shoe prints and heights. Now, in a scatter plot, an outlier is a point lying far away from the other data points. So again, just pretty general definition of an outlier. Then the paired sample data may include one or more influential points, which are points that strongly affect the graph of the regression line. So just some other definitions there. Basically, an influential point will just be a big outlier. And these could be some hypothetical scatter plots of the 40 pairs of shoe prints and heights mentioned before. And then, so this is the original scatter plot here, just a nice line, and as if we had 40 dots here for shoe prints and heights. Now, notice what happens if we add the point 35 centimeters for a shoe print and then 25 centimeters for a height. So this point down here, so this could be considered an influential point or an outlier, because once we put that point in there, it throws off the rest of the scatter plot quite a bit. Because before the scatter plot was kind of going up and to the right a little bit, nice positive linear pattern. Now the rest of the scatter plot looks like it's mostly going horizontal. And of course, an influential point like this would probably be ridiculous in real life, because with those measurements, it's probably just the measurements of like a big shoe or just a foot or something like that. But again, that's just to kind of give you an idea of what an influential point looks like. Now, continuing with that, the additional point is an influential point because the graph of the regression line, the graph of the regression line did not change considerably. Sorry, I didn't notice that was typed in there twice. All right, the additional point is also an outlier because it is far from the other points. And some more definitions here. For a pair of sample x and y values, the residual is the difference between the observed y value and the y value that is predicted from the regression equation. And so again, just kind of putting that into an equation notation here. Residual equals observed y minus predicted y, or y minus y hat for some other notation. And so the residuals, say for an example like this, where here's just a scatter plot of 4 points, and the regression equation could be y hat equals 5 plus 4x, but the actual points show the residual or difference with this actual point is 7, this actual point it's 11, this actual point is negative 13, and this actual point is negative 5. Again, notice this is always, to get the residual, it's always the actual point minus the predicted point that would be on the line. And so because this point is above the line here, the residual is positive. Because these points are both below the line, this actual point minus this predicted point on the line, that difference would be negative. All right, and then a straight line that satisfies the least squares property if the sum of the squares of the residual is the smallest sum. And so this is partly why the regression line may also be called the least squares line, as we saw from before, because if these squares are all the smallest possible sum we can get, then this is the best fit line because it'll have all the smallest residuals. And we use the squares of all those residuals because if we have, say, an even amount of negative and positive residuals, they're just going to cancel each other out to zero if we didn't square them. And so say there was like a really big point up here and a really small point down here. Well, if we didn't square them, their residuals wouldn't matter because they'd kind of be zeroing each other out. Now, just with another definition here, so a residual plot is a scatter plot of the xy values after each of the y coordinates has been replaced by the residual value that you get from doing the observed minus the predicted y value. And that is a residual plot is a graph of the points x, comma, y minus y hat. Now, when you analyze residual plots, then actually, before me talking about the analysis, just keep in mind that the stat-semantic applets we used from before, when you click on to generate the regression models, those automatically come up with the residual plots for you. So notice this is a plot of where it was 17 pires and the residual is 0.355. So that's taken for at this point. Sorry, no, so this point, didn't scroll far enough. So for this point, going from that difference to the line there, its residual is 0.355. And you can look at that for any of the points there. Then it gives you one more graph here on that applet that's just the residuals with no x scale. All right, and then just continuing with the analysis from there. So when analyzing a residual plot, look for a pattern in the way the points are configured and use these criteria. The residual plot should not have any obvious patterns, not even a straight line pattern, as this will confirm that the scatter plot of the sample data is a straight line pattern. Then the residual plot should not become thicker or thinner when viewed from left to right. This confirms the requirement that for different fixed values of x, the distributions of the corresponding y values all have the same standard deviation. And so that's just kind of a fancy way of saying with both of those paragraphs that we want it to just kind of stay closest to zero for the residual plots. So like, for example, this is a residual plot from the 5 pairs of shoe prints and heights from before. Notice it's going like wider in both directions. And if we want it to be a good residual plot, we want them to all be kind of like staying pretty close to zero, because that would mean that our line would be fit pretty good because there aren't very many differences. And so since that residual plot becomes thicker, that just suggests that the requirement of equal standard deviations is violated. Just, again, a fancy way of saying it's just not a good fit, that regression line. Now, on the following slides, there are 3 residual plots, and then so we'll take a look at how we can tell that they're good or bad regression models based on the residual plots. So like this would be a pretty good residual plot, just showing that it's coming from a good model. There's no distinct pattern here, and all these residuals are staying relatively close to zero. And since this residual plot is following some sort of a distinct pattern, looks like kind of a wave pattern, then that shows that the regression equation itself that you would get this residual model from is not a very good regression equation. And same idea here, since the residuals get wider, then it shows that the regression equation just must not be a very good fit. Now, again, there's further things you can do with the regression analysis. We won't need to worry about too much more rather than just seeing if the residuals stay pretty close to zero. And I'll just read over these first 2 here. So just to go through the analysis steps, just go ahead and construct your scatter plot. Verify that if the points follow an approximate straight line pattern with hopefully no outliers, then you can construct the residual plot. And hopefully there's no pattern, it's not becoming thicker, they're all staying relatively close to zero. And you could take it further with making a histogram or a normal quantile plot to confirm that the values of the residuals have a distribution that is approximately normal. But again, just what we'll be doing is just kind of making sure that they all stay relatively close to zero. So like for example, between looking at the pirates and global temperature data, again, these residuals are all staying pretty darn close to zero. There's no obvious pattern as to what the residuals are doing. Whereas when I look at the shoe and height data from before, just the 5 pairs, then yeah, notice that residuals, or those residuals are getting wider as they go out. So this one's just not very good. But this residual plot shows this regression equation is not a good fit. Whereas this residual plot shows that this regression equation is a fairly good fit.